Welcome back to Aram Dev Hub. In this video, we'll be building a comprehensive authentication system in Rust using Actix-Web. We'll cover everything from setting up the project to adding Swagger UI for interactive API documentation. By the end of this video, you'll have a fully functional authentication API that you can test and explore using Swagger UI. Here's a brief overview of what we'll be building in this video. We'll start by creating a new Rust project and setting up our development environment. We'll define our database model, create the schema, and run migrations to set up our PostgreSQL database. We'll configure environment variables for database and JWT settings. We'll connect our Rust application to the PostgreSQL database using SQLx. We'll implement error handling for our API endpoints. We'll create DTOs to structure the data for our API requests and responses. We'll build functions for hashing passwords and handling JWTs. Hashing and comparing passwords. Signing and verifying JWTs. We'll implement functions to interact with the database. We'll set up middleware to protect our endpoints. We'll create endpoints for user registration, login, and logout. We'll build endpoints to retrieve user information. We'll configure CORS to allow requests from different origins. We'll integrate Swagger UI for interactive API documentation. Registering the OpenAPI schema. Registering the API handler as OpenAPI path. Generating the OpenAPI base object. Serving the Swagger UI via a web server and much more. First, let's see a quick demo of what we are building in this video. First, we need to create a .env file in the root directory of your Rust project. This file will store our environment variables, which include the database connection URL and JSON web token, JWT, credentials. Database URL. This is the connection string for our PostgreSQL database. Replace password with your actual PostgreSQL password. JWT secret key. This is the secret key used for signing JWTs. Make sure to use a secure and unique key. JWT-MAXAGE. This sets the maximum age, in minutes, for the JWT before it expires. Next, we need to install SQLx-CLI, a command line tool for managing SQLx migrations. This command installs the SQLx command line interface with support for PostgreSQL. No default features Postgres. These flags ensure that we only install the PostgreSQL feature set, which is what we need for our project. Let's add the step for including all the necessary dependencies in your Rust project's cargo, toml file. This will ensure that your project has all the libraries required for your web server, database interactions, JWT handling, and more. In your Rust project, open the cargo, toml file and add the following dependencies under the Dependencies section. Actix-Cos provides CORS, cross-origin resource sharing, support for Actix-Web. Actix-Web, web framework for Rust, used to create the HTTP server. Argon 2, library for hashing passwords securely using Argon 2. Async trait, enables async support for traits. Chrono, date and time library for Rust, with surge support for JSON serialization, deserialization. .env, loads environment variables from a .env file. env_logger, provides logging capabilities for debugging. Futures util, utilities for working with asynchronous programming in Rust. JS on Web Token, library for creating and verifying JSON web tokens, JWT. OpenSSL probe, a library to probe for OpenSSL installation. Serd and Serd_JSON, libraries for serializing and deserializing data. SQLx, an async SQL crate for PostgreSQL, with support for various features including TLS and UUIDs. Autoipa, Autoipa Rapidoc, Autoipa Redoc, Autoipa Swagger UI, libraries for generating API documentation and using Swagger, Rapidoc, and Redoc with Actix-Web. UUID, a library for working with UUIDs, including surge support. Validator, provides validation capabilities for structs using attributes. First, add a new migration to create the users table. This will generate a new migration file where you can define your table schema. SQLx migrate add r_user_table. This command creates a new migration file with the name user_table. The R flag indicates that you are creating a new migration. After running the command to add a new migration, SQLx generates two files in the migrations directory. User_table, up.sql, the up migration file for applying changes. User_table, down.sql, the down migration file for reverting changes. Navigate to the migrations directory in your project. You'll find the newly created files with timestamps in their names, which are used to ensure the order of migrations. Edit the user_table, up.sql file. Define the schema changes to apply to the database. This includes creating tables, columns, indexes, and other schema elements. Create type user_role as enum, admin, moderator, user. Defines an enum type named user_role for user roles. This ensures that only the predefined values, admin, moderator, user, can be used. Create extension if not exists, UUIDOSSP. Creates the UUIDOSSP extension if it is not already present. This extension is necessary for generating UUIDs. Create table, users. Creates the users table with the following columns, id, a UUID that serves as the primary key, with a default value generated by UUID_generate_v4. Name, a varchar field to store the user's name, which cannot be null. Email, a varchar field for the user's email, which must be unique. Photo, a varchar field for storing a photo URL, with a default value of default.png. Verified, a boolean field indicating whether the user's email is verified, defaulting to false. Password, a varchar field for the hashed password, which cannot be null. Role, an enum field using the user_role type to define the user's role, defaulting to user. Created_at, a timestamp field with time zone to record when the user was created, defaulting to the current time. Updated_at, a timestamp field with time zone to record the last update time, defaulting to the current time. Create index users_email_idx on users, email. Creates an index on the email column to speed up queries that filter by email. Edit the user_table down.sql file. Define how to revert the schema changes if needed. This file should undo all changes made by the up migration. Drop table if exists, users. Removes the users table if it exists, effectively deleting all user data and schema. Drop type if exists user_role. Drops the user_role enum type if it exists, removing it from the schema. Drop extension if exists, uuidossp. Drops the uuidossp extension if it is not used by other parts of the schema. By editing these migration files, you ensure that your database schema is properly set up and can be managed through version migrations. The up migration applies the changes, while the down migration provides a way to roll back those changes if needed. This approach helps in maintaining a consistent and manageable database schema throughout the development lifecycle. Ensure PostgreSQL is running and your .env file is properly configured with the database URL environment variable. Run the following command to create the database. This command reads the database URL from your .env file and creates the database specified in it, e.g., Rust Auth. Apply the migration to your database. This command applies all pending migrations, including your newly added user_table migration, to your database. In this section of our video, we'll be creating the models.rs file for our Rust project. This file defines our data models that will interact with the database. Let's dive into the code and understand how it works. Let's start by looking at the import statements at the beginning of our file. Chrono, prelude, asterisk, this imports date and time utilities from the chrono crate, which is used for handling timestamps in our data models. Third, deserialize, serialize, these traits are used for converting our data models to and from JSON. This is essential for serialization and deserialization of data, especially when working with APIs. Next, let's look at the user role enum. Debug allows the enum to be formatted with, which is useful for debugging. Deserialize and serialize, these traits enable the enum to be converted to and from JSON format. Clone and copy supports copying the enum values. SQLx type integrates with SQLx to map this enum to a PostgreSQL type. Partial EQ allows comparison of user role values. Hash SQLx type underscore name equals user underscore role, rename underscore all equals lowercase. Type underscore name equals user underscore role maps the Rust enum to the PostgreSQL enum type user underscore role. Rename underscore all equals lowercase ensures that the enum values are stored in lowercase in the database. The user role enum represents different roles that a user can have in the system: admin, moderator, and user. Now, let's look at the implementation block for the user role enum. To underscore str method converts the enum variant to its string representation. Match self checks the variant of user role and returns the corresponding string. This method is useful when you need to get a string representation of the user role for displaying in the user interface or logs. Let's now examine the user struct. Debug for formatting the struct with. Deserialize and serialize for converting the struct to and from JSON format. SQLx from row allows the struct to be populated from SQL query results. SQLx type integrates with SQLx for database operations. Clone allows cloning of the struct. Id, a unique identifier for the user, represented as a UUID. Name, the user's name. Email, the user's email address. Password, the user's hashed password. Role, the user's role, using the user role enum. Photo, URL or path to the user's profile photo. Verified, Boolean indicating whether the user is verified. Created underscore at and updated underscore at, optional timestamps for when the user was created and last updated. These fields are renamed using third attributes to match the JSON format. The user struct directly maps to the columns in our users table in the database. The third attributes ensure that the field names match the JSON keys when sending or receiving data. That's a wrap on the models.rs file. We've defined our user roles and user data model, which are crucial for interacting with our database. In the next section of the video, we'll move on to integrating these models into our application logic. In this section, we'll be creating the config.rs file for our Rust project. This file will handle configuration settings, including database connections and JWT credentials. Let's dive into the code and see how it works. Let's start with the definition of the config struct. Debug allows the struct to be formatted with, for debugging purposes. Clone enables cloning of the struct. Database URL holds the URL for connecting to the database. JWT secret stores the secret key used for signing JWTs. JWT maxage specifies the expiration time, in minutes, for the JWT. Port defines the port number on which the server will run. This struct will be used to store and access our configuration settings throughout the application. Now, let's look at the implementation block for the config struct. Init method. This function initializes a new config instance. std, env, var, retrieves environment variables. If a variable is not set, it will panic with an appropriate error message. Database URL, the URL for the database connection. JWT secret key, the secret key for JWT. JWT maxage, the maximum age for the JWT, read as a string and then passed to I64. Pass, less than I64 greater than, converts the JWT maximum age from a string to an I64 integer. If parsing fails, it will panic. Port 8000 sets a default port number for the server. The init method ensures that all necessary configuration settings are loaded from environment variables and provides default values where applicable. In this section of the video, we'll be creating the DTOs.rs file, which plays a crucial role in defining how data is transferred within our Rust application. DTOs, or data transfer objects, help us validate and structure the data exchanged between different parts of our application. Let's dive into the code and understand each part step by step. First, let's start by importing the necessary dependencies for our DTOs. Chrono provides the date, time and UTC types for handling date and time. Serd allows us to serialize and deserialize data structures, making it easy to convert them to and from JSON. Autoipa helps in generating open API documentation for our DTOs, making them easier to understand and use in APIs. Validator provides a way to validate incoming data against specific criteria. User we import the user struct from our models.rs file to use it in one of our DTOs. Next, we define the register user DTO, which will validate the data when a user registers. Name must not be empty. Email must be a valid email address and not empty. Password must be at least 6 characters long. Password_confirm must match the password field. These validation rules ensure that the data provided during user registration is complete and valid before it's processed. Similarly, we define login user DTO for validating user login data. Email must be a valid email address and not empty. Password must be at least 6 characters long. This ensures that the login data is properly validated, avoiding any errors during the login process. Next, we create the request query DTO, which helps handle pagination for API requests. Page must be at least 1. Limit must be between 1 and 50. This DTO is useful for managing paginated API responses, making it easier to work with large datasets. Now, let's create filter user DTO, which will structure user data for API responses. Filter user DTO converts the user struct into a format that's ready to be sent as an API response. We also create methods to transform a user struct into a filter user DTO and to convert a list of user structs into a list of filter user DTOs. These methods ensure that the user data is properly formatted before it's sent out via an API. User data is a simple wrapper struct that contains a single filter user DTO. It's useful for grouping user data under a user field in API responses. User response DTO structures the response for API requests that return a single user. The status field indicates success or failure, and the data field contains the user data. User list response DTO is used when the API needs to return a list of users. The users field contains a vector of filter user DTO, and the results field indicates the total number of users returned. After a successful login, user login response DTO is used to return a status message and a JWT token, which the client can use for authenticated requests. Response struct is used for general responses that don't need to return specific data, just a status and a message. In this step, we'll create an error.rs file to define how our application handles errors. Proper error handling is crucial for providing meaningful feedback to users and developers. This file will include custom error types, error messages, and the conversion of errors into HTTP responses. First, let's start by importing the necessary dependencies for our error handling module. FMT provides functionality for formatting and displaying custom errors. Actix-Web, we use HTTP response and response error to convert errors into HTTP responses. CERD enables serialization and deserialization of error responses to and from JSON. Response, imported from our DTOs module, allowing us to structure error responses. Error response struct defines the structure of the error response that will be sent to the client. Status indicates the status of the response, typically fail or error. Message, a description of the error. FMT, display for error response. This implementation allows us to convert error response into a JSON string, making it easier to display or log errors in a readable format. The error message enum defines various error types that our application might encounter. Variants, each variant represents a specific error, such as empty password or wrong credentials. Some variants, like exceeded max password length, use size, can carry additional data. To string and into less than string greater than implementations allow us to easily convert an error message into a string. This is useful when we need to convert errors into a format suitable for logging or displaying. Error message to _str method maps each error message variant to a user-friendly error string. This string can be sent in the HTTP response or logged for debugging. The HTTP error struct represents an HTTP error, including a message and status code. Fields, message, a detailed description of the error. Status, the HTTP status code, e.g., 400 for bad requests, 500 for server errors. Custom errors, methods like server_error, bad_request, unique_constraint_violation, and unauthorized allow for easy creation of common error types. Conversion to HTTP response. The into_HTTP_response method converts an HTTP error into an HTTP response that can be sent to the client. The FMT display implementation formats the error message, making it easier to log or display the error. Error trait. By implementing std error, HTTP error becomes compatible with Rust's error handling ecosystem. Response error for HTTP error implementation allows HTTP error to be directly returned as an HTTP response in Actix-Web handlers. The error_response method converts the error into an appropriate HTTP response based on its status code and message. By setting up the error.rs file this way, you create a robust error handling system that not only provides clear feedback to the users of your API but also ensures that developers can easily identify and address issues during development and production. First, create a new folder in your project directory called utils. This folder will house utility functions and modules that can be reused across your application. Inside the utils folder, create a file named mod.rs. This file will serve as the entry point for any modules you define in the utils folder. Here, we are defining a module named password inside the utils folder. The pub mod password statement tells Rust that there is a password.rs file in the same folder that we want to include in the module system. This makes the password module publicly accessible to the rest of the application. Now, create a file named password.rs inside the utils folder. This file will contain functions to handle password hashing and verification. First, let's start with the imports. Argon2. We're using the Argon2 crate, a popular and secure password hashing algorithm. It's widely regarded as one of the safest algorithms for storing passwords. Password hash, rand_core, OSRNG, password hash, password hasher, password verifier, salt string, OSRNG. This is a random number generator used to create a secure, random salt for hashing passwords. Password hash, password hasher, password verifier, salt string. These traits and structs help in generating and verifying password hashes. They manage the complexity of handling cryptographic operations, making it easier to securely store passwords. Argon2. This is the main struct that implements the Argon2 password hashing algorithm. We'll use it to hash and verify passwords. Use crate, error message. This line imports the error message enum from your project's error handling module. It defines the custom error types that our password functions will return, such as empty password, exceeded max password length, and hashing error. Next, we define a constant. This constant defines the maximum allowed length for passwords, set to 64 characters. Limiting the password length helps prevent certain types of attacks and ensures that the hashing process remains efficient. Now, let's write the hash function. Pub fn hash, password, impl into less than string greater than, to result less than string, error message greater than. This is a public function that takes a password as input and returns either the hashed password as a string or an error message. Password validation. Empty password check. If the password is empty, the function returns an error message, empty password. Length check. If the password exceeds the maximum length, it returns an error message, exceeded max password length. Generating the salt string, generate, and mut OSRNG. This generates a secure, random salt using OSRNG. Hashing the password. Argon2, default, hash_password, password.as_bytes, and salt. The password is hashed using the Argon2 algorithm along with the generated salt. If the hashing process fails, it returns an error message, hashing error. Returning the hashed password. If successful, the hashed password is returned as a string. Finally, let's write the compare function. Pub fn compare, password, and str, hashed_password, and str, to result less than bool, error message greater than. This function compares a plain text password with a previously hashed password. It returns either true if they match or false if they don't, along with any relevant errors. Password validation. Similar to the hash function, we check if the password is empty or exceeds the maximum length, returning the appropriate error if so. Parsing the hashed password. Password hash. New, hashed_password. This attempts to parse the stored hashed password. If the format is invalid, it returns an error message, invalid hash format. Verifying the password. Argon2, default, verify_password, password.as_bytes, and parsed_hash. This function compares the plain text password with the parsed hash. If they match, it returns true, otherwise, false. In this section, we'll continue building our Rust project by creating the token.rs file in the utils folder. We'll be writing code to generate and decode JWT tokens, which are essential for handling user authentication. Let's dive in. First, let's start with the imports. Chrono. This module helps us work with dates and times. Duration. We'll use this to define the expiration time for the JWT token. UTC. This represents the current time in UTC format, which is necessary for setting the token's issued and expiration times. JS on Web Token. This library is used for creating and validating JWT tokens. Encode, decode. These functions allow us to create and verify JWT tokens. Algorithm. This specifies the algorithm we'll use, in this case, hydrogen sulfide. Decoding key, encoding key. These are the keys used for encoding and decoding the tokens. Header. This defines the JWT header. Validation. This is used to validate the token. CERD. This library allows us to easily convert our data to and from JSON format. Deserialize, serialize. These traits let us serialize and deserialize our token claims struct to JSON, which is necessary for encoding and decoding the token. Create, error, error message, HTTP error. These are custom error types from our project's error handling module, used to handle any errors that occur during token creation and decoding. Next, we define the token claims struct. Token claims. This struct represents the payload of our JWT token. Sub. This is the subject of the token, usually the user ID. IAT. This is the issued at timestamp, marking when the token was created. Express. This is the expiration timestamp, indicating when the token will expire. Hash, derive, debug, serialize, deserialize. Serialize and deserialize allow us to convert the token claims struct to and from JSON format. Debug allows us to easily print the struct for debugging purposes. Now, let's write the create underscore token function. Function signature. User underscore id. The ID of the user for whom the token is being created. Secret. The secret key used for encoding the token. Expires underscore in underscore seconds, the duration for which the token will be valid. The function returns either the encoded token as a string or an error. Validation. The function first checks if user underscore id is empty. If it is, we return an invalid subject error. Token creation. UTC. Now, captures the current time. IAT. The current timestamp, representing when the token was issued. Express. The expiration timestamp, calculated by adding the specified duration to the current time. Token claims struct. This struct is filled with the user underscore id, IAT, and express values. Encoding the token. Encode, and header, default, and claims, and encoding key. From underscore secret, secret. This encodes our token claims struct into a JWT token using the provided secret key. Finally, let's write the decode underscore token function. Function signature. Token, the JWT token that we want to decode. Secret, the secret key used to decode the token. The function returns either the sub, user ID, from the token claims or an error. Decoding the token. Decode, less than token claims greater than, and token, into, and decoding key, from underscore secret, secret, and validation. New algorithm, HS256, this decodes the token and validates it against the secret key. Validation. If the token is successfully decoded, we extract the sub, user ID, from the claims and return it. If decoding fails, we return an HTTP error with a 401 status code, indicating that the token is invalid. That's how you can create and decode JWT tokens in Rust using the JS on Web token crate. This is a crucial part of handling user authentication in your web applications. In this section, we'll be creating the db.rs file, where we'll handle interactions with our PostgreSQL database using SQLx. Let's get started. First, let's start by importing the necessary libraries and modules that we'll need for our database operations. First, let's start by importing the necessary libraries and modules that we'll need for our database operations. Imports the user role enum from the models module. We'll use this to manage different user roles, such as admin and user. Brings in the async_trait macro, allowing us to define async functions within our traits. This is crucial because Rust's trait system doesn't natively support async functions. Imports pool and Postgres from the SQLx library. Pool will manage our connections to the PostgreSQL database. Imports UID, which we'll use for generating unique user IDs. Imports the user struct from the models module, representing our users in the database. Next, we define the DB client struct. This struct will be our main entry point for interacting with the database. DB client holds a connection pool to our PostgreSQL database, ensuring that our database operations are efficient and scalable. The new function allows us to create a new instance of DB client by passing in a connection pool. Now, let's define a trait called user_ext. This trait will contain the methods we'll use to interact with our users table in the database. GetUser retrieves a user by their ID, name, or email. This is useful for searching for specific users in our database. GetUsers retrieves a list of users with pagination, making it easy to manage large datasets. SaveUser inserts a new user into the users table. This is a fundamental operation for registering new users. SaveAdminUser works similarly to SaveUser but assigns the admin role to the user being created. Finally, we implement the user_ext trait for our DB client. This is where we define the actual logic for interacting with the database. The getUser method is implemented to fetch a user by ID, name, or email using SQL queries. GetUsers fetches a paginated list of users, allowing for efficient data retrieval in large tables. SaveUser inserts a new user into the database and returns the created user. SaveAdminUser does the same as SaveUser but assigns the user an admin role. In this section, we are going to focus on our main.rs file. This is where we configure and run our Actix-Web server. We'll walk through the code, explaining how it sets up the server, connects to the database, and integrates various components. Let's dive in. First, let's review the imports at the top of our file. Actix-Cos. Cos is used to configure cross-origin resource sharing (CORS) settings. Actix-Web brings in various components for building the web server, including middleware and HTTP utilities. Config loads configuration settings from environment variables. DB client is our database client for interacting with the database. .env .env loads environment variables from a .env file. DTOs imports various data transfer objects, DTOs, used for request and response handling. SQLx, Postgres, PG pool options configures connection pooling for PostgreSQL. Autoipa and related crates are used for generating and serving API documentation. Next, we define the app state struct, which will hold our application state. App state contains the application's configuration and database client, allowing us to share state across our handlers. We then define the API doc struct for our API documentation. OpenAPI is used to generate OpenAPI documentation for our API endpoints. Paths lists all the endpoints included in our documentation. Components specifies the data schemas used in the API. Tags provide metadata about our API. Modifiers and security add-on applies custom modifications to the OpenAPI specification. Now, let's look at the security add-on struct and its implementation. Security add-on adds a security scheme to our OpenAPI documentation to specify that our API uses bearer tokens for authentication. Next, let's configure and start our Actix server in the main function. OpenSSL probe, init SSL cert env initializes OpenSSL for SSL, TLS certificates. We set the logging level to Actix-Web equals info if not already set. .env, OK, loads environment variables from a .env file. env logger, init, initializes logging. We create a connection pool to PostgreSQL using PG pool options and apply any pending migrations. DB client, new, pool, initializes our database client. We print the server URL and set up OpenAPI documentation. HTTP server, new configures our server with CORS, logging, and API documentation endpoints. App, new, sets up our application with all the configured services and routes. Finally, let's examine the health check endpoint. Hash, autoipa, path, provides OpenAPI documentation for the endpoint. Hash, get, API, health checker, defines the route for our health check. Health checker handler returns a JSON response indicating the server status. We've walked through the main.rs file, from setting up the server and database to defining our API documentation and health check endpoint. In this section, we'll go through the code for the auth.rs file, which handles the authentication middleware for your Rust-based API. This file plays a crucial role in ensuring that only authorized users can access certain endpoints in your application. We start by importing necessary modules and structs from Actix-Web, a powerful framework for building web applications in Rust. Futures util provides combinators to work with asynchronous code. RC from the std. RC module is a reference counted pointer used to share data between different parts of your application. Custom modules like user ext, error message, and others are imported to handle database interactions, error management, and user roles. Authenticated is a wrapper around the user struct, representing a user who has been successfully authenticated. The from request trait implementation allows extracting the authenticated struct from an incoming HTTP request. It checks if a user is attached to the request. If not, it returns an internal server error. The deref implementation allows you to access the user directly from the authenticated struct, making it easier to use. Require auth is a struct that holds the roles allowed to access a particular resource. It uses RC to share the roles across different parts of your application. The allowed roles method is a constructor that initializes the require auth struct with a list of allowed roles. The transform trait allows you to transform a service into another service. Here, it is used to add an authentication layer, auth middleware, on top of your existing service. New transform is used to create a new instance of the auth middleware, which will enforce authentication based on the roles specified. Auth middleware is the core part of your authentication system. It checks if the user is authorized to access a particular resource based on the roles allowed. Poll_ready ensures the service is ready to process requests. Call is where the actual authentication happens. First, it retrieves the JWT token from either the cookie or the authorization header. If the token is not provided, it returns an unauthorized error. The token is then decoded to extract the user ID, and the corresponding user is fetched from the database. If the user exists and their role is allowed, they are attached to the request and the service is called. Otherwise, a forbidden error is returned. This code ensures that only authenticated users with the appropriate roles can access certain parts of your application. Each part is designed to handle specific tasks, from extracting and verifying tokens to checking user roles and managing middleware transformations. In this section, first create handler folder in your project root directory. In your handler folder, start by creating a mod.rs file to manage module imports. The mod.rs file will allow you to organize and structure the auth.rs file, making it accessible to other parts of your project. In mod.rs file add pub mod auth. This line of code declares the auth module, which contains the authentication logic defined in the auth.rs file. The auth.rs file handles all the authentication-related routes and logic. Here's a breakdown of the code. These imports are essential for managing requests, responses, cookies, validation, error handling, and user-related data. Auth handler defines the API auth endpoint with three routes: register, login, and logout. Require auth allowed roles wraps the logout route with a middleware that checks if the user has the required role. Register handles user registration. Validation. The input is validated using validate from the validator crate. Password hashing. Passwords are hashed for security using a utility function. Database insertion. The user is saved to the database. Error handling. Unique email constraint violations and other errors are handled. Login manages user login. Password matching compares provided password with the hashed password stored in the database. Token generation generates a JWT token if the login is successful. Cookie creation stores the token in an HTTP-only cookie. Logout invalidates the JWT token by setting its expiration to the past. This auth.rs file is essential for handling the core authentication processes, registration, login, and logout. Each function is integrated with the rest of your application using the auth handler function, which provides a clean and modular structure. In this section, we will create a new file called users.rs within the handler folder of our Rust project. This file will handle the roots and logic related to user management, such as retrieving the authenticated user's details and fetching a list of all users. Let's dive into the code that will go into this file. Actix-Web, Web, HTTP response, scope. These are the essential imports from the Actix-Web framework, used to define routes, web, send responses, HTTP response, and create scopes, scope. Validator, validate. We use this to validate incoming request data. The rest of the imports are from our project's modules, including database access, DB, user ext, data transfer objects, DTOs, error handling, error, HTTP error, authentication, auth, authenticated, require auth, and models, user role. Next, we define the scope for the user-related routes. Users handler function. This function creates a scope for the API users endpoint. Inside this scope, two routes are defined: get API users. This route fetches a list of all users, and it's wrapped with require auth to ensure only users with the admin role can access it. Get API users me. This route retrieves the authenticated user's information. It is accessible by users with the user, moderator, or admin roles. Now, let's implement the getMe function, which retrieves the currently authenticated user's information. GetMe function. This function is triggered when a GET request is made to API users me. The function uses the authenticated extractor to get the authenticated user's details. It then filters the user's data using filter user DTO, filter user, which removes sensitive information. Finally, it returns the filtered user data wrapped in a user response DTO within an HTTP response, OK, response. Finally, let's implement the getUsers function, which retrieves a paginated list of all users. GetUsers function. This function is triggered when a GET request is made to API users. It accepts query parameters like page and limit to control pagination. The query parameters are validated using the validate trait. It then retrieves the users from the database using app-state, dbclient.getUsers. The result is returned as a user list response DTO within an HTTP response, OK, response. That's it. We've successfully created the users.rs file in the handler folder, defined user-related routes, and implemented the necessary logic to handle these routes. This file will help manage user information securely, ensuring that only authorized users can access or modify certain data. In this final section of our video, we'll be editing the main.rs file to integrate the authentication and user management handlers we've implemented. This step is crucial as it connects all the pieces of our backend application, ensuring that the routes for authentication and user management are properly set up and ready to handle requests. At the top of the main.rs file, make sure to import the auth and users modules from the handler module. This import brings the auth and users modules into scope, allowing us to register their respective routes with the Actix-Web application. Next, let's update the app new block to include the authentication and user management handlers. Locate the existing code that sets up the Actix-Web application and edits. Service handler, auth handler. This line registers the authentication routes, allowing your application to handle login, registration, and other authentication-related requests. Service handler, users scope. This line registers the user management routes, enabling your application to handle requests related to user data, such as retrieving user details or listing all users. And that's a wrap. We've now completed the integration of our authentication and user management functionalities into the main.rs file. By adding these handlers, we've successfully linked all the key components of our backend application, making it fully functional and ready for test. It's time to see all our hard work in action. We're going to run the code we've written, test our endpoints, and ensure everything is functioning as expected. In your browser's address bar, type http://localhost port 8000 and hit enter. As you can see, we are greeted with the Swagger UI. This interface provides a visual representation of our API's endpoints, making it easier to interact with and test them directly from the browser. Here, you can see all the endpoints we've created, like the user registration, login, and user management endpoints. Each endpoint is documented with details on the request parameters, responses, and possible error codes. Let's try out one of these endpoints directly from the Swagger UI. And that's a wrap. We've built a robust authentication system in Rust, integrated Swagger UI for documentation, and explored various middleware techniques. If you found this video helpful, please give it a thumbs up, subscribe to Aram Dev Hub, and hit the notification bell for more content. Thanks for watching, and happy coding!